Okay, so we might as well, oops, get rid of that. We might as well start. This is the first lecture of the morning in Tokyo. And the first lecturer is Professor Bhargav Bhatt from the University of Michigan. And his title is P-adic cohomology theories via stacks.
Great, thank you. Thank you very much for the introduction and also for this very kind invitation to speak here. It's a great honor for me to be speaking at this conference for Takeshi Saito. So I've learned a lot of math from reading his papers. But in the last few years, he's been thinking about things that are sort of closer to some of the things I've thought about, in particular, this notion of Frobenius-Witt differentials. And so I was very happy about this. So I now have the opportunity to, at the end of my talk, at least speculate about a more concrete connection between this theory of Frobenius-Witt differentials and something more along the lines of stuff I've done. Okay, great. So let me get started. So as I wrote in my notes on the screen, everything I'm talking about that's new is joined with Jacob Lurie, and everything that I say is independently due to Drinfeld, either in written form or otherwise. And so the goal of what I want to explain today is how one goes about thinking about Durham-style cohomology theories in algebraic geometry through stacks. And I will try to convince you as we go along that there's some value in doing this. So some natural structures on those cohomology theories can be seen very easily from the stacky side. And eventually, I'll give 4 examples. And then in the 4th example, we'll see that actually the stacky approach is the one that tells you about these structures that you wouldn't have seen otherwise. But so I want to start just in a simple situation, so in characteristic 0. And maybe even before I start, I should begin with an apology. So probably the most interesting results in this talk will be the definitions rather than the actual theorems I'm writing down. And so I'm sorry for that, but I just wanted to explain where some of these ideas came from. Okay, let's get started. So let's begin with Durham cohomology just in characteristic 0. Everything I'm talking about is algebraic, so I might as well just work over any field of characteristic 0. So fix a field K of characteristic 0. And my goal is to explain how one goes about thinking about the Durham cohomology of a smooth variety over K in terms of the coherent cohomology of a certain associated stack. And so this is all, in characteristic 0, this is all due to Simpson and also following ideas of Deligne. And so they had this idea of defining the notion of a Durham space of a variety. And then once you have the Durham space, you can produce a Durham cohomology out of it. And I want to sort of recount how this story goes and also tell you how you might see the Hodge filtration this way. So the sort of starting point is the following construction, which is implicit in the definition of the Durham space. And I will try to make it explicit now. So this is what I will call GA Durham. It's a gadget that will that will intervene in the definition of the Durham space. And it's defined as follows. So GA hat is going to be my notation for the formal additive group. So it's the formal spectrum of K power series T. I'm going to think of everything in section 1 as functors or as presheaves on the category of K algebras. And so this is really a subfunctor of GA, which is a spec of K polynomial ring T. And in fact, it's slightly better than that. It's actually an ideal. And so the easiest way to sort of understand what's going on is to just look at the functor of points. And so let me remind you, so the functor of points of GA hat, so GA hat evaluated on a ring R is just the nil radical of the ring. And this is obviously an ideal of the ring, just GA evaluated on R. And so we have a presheaf of rings, and then we have a presheaf of ideals, so we can form the quotient. And so I'll call that GA Durham. It's going to be GA mod GA hat. This is as, let's say, as étale sheaves on K algebras. So I don't want to think about it as a some kind of algebra geometric object like a variety will be very non-separated and so on. But it makes complete sense as a sheaf. I'm implicitly using the étale topology when I say sheaf, although you're free to use your favorite choice of topology. It's something like FPPF would also work. And so this is now a sheaf of rings. And we're going to use the sheaf of rings to sort of, so what I want to explain is that this sheaf of rings packages all the information of Durham cohomology of smooth varieties, all the functorial information. And so here's how you make that precise. So here's the definition, which is the definition of the Durham space. So let's say X over K is a smooth variety. Then I'm going to define this new gadget, which is called the Durham space of X, X Durham. This is also going to be a pre-sheaf on K algebras. And so its functor of points is given as follows. So X Durham evaluated on a ring R is X evaluated on GA Durham evaluated on R. Okay, and so very concretely, what this means is that it's X evaluated on R modest nil radical, or equivalently R reduced. So I'm implicitly asserting here that the functor evaluating GA Durham on rings gives you the obvious object, R reduced. So it's just this is a definition. It's a perfectly sensible thing to define. And the sort of miracle, or the first time you see it, I think it's a miracle, is the following theorem due to Simpson that says that the Durham cohomology of X is actually just the coherent cohomology of X Durham. So there's a natural isomorphism between the Durham cohomology of X over K, the algebraic Durham cohomology, and the coherent cohomology of X Durham, so cohomology of the structure sheaf. And so maybe I should say that whenever you have a pre-sheaf or a sheaf on the category of K algebras, it makes sense to talk about its cohomology with coefficients in O, because O is another sheaf on K algebras, and there's this general machinery of taking cohomology of a pre-sheaf with coefficients in a sheaf. And so that's what I mean over here. And so this is a coherent object, and this is the Durham object, and the assertion is that the two are isomorphic. And moreover, this isomorphism extends to sort of fancier things. So for example, on this side, there's a natural notion of coefficients, which is modules with integrable connection. And on this side, there's a natural notion of coefficients, which is vector bundles or quasicoherent sheaves, if you want to allow big objects. And those are going to match up as well. And so it's really kind of a robust equivalence between the two approaches to doing Durham cohomology. And so later in the talk, I want to explain how this works in mixed and positive characteristic. But before I do that, I wanted to sort of tell you how you might see certain structures on Durham cohomology through this isomorphism. So in characteristic 0, as we are, Durham cohomology has is not just a vector space, or it's not just a complex of vector spaces. It has certain additional structures. Probably the most important one from the algebraic point of view is the Hodge filtration. So this is naturally defined as the cohomology of a complex of sheaves. And so if you use the the stupid filtration on the complex, it induces a filtration on the cohomology, which is the Hodge filtration over here. And so let's try and understand what that means on this side. So we're supposed to produce a natural filtration on the coherent cohomology of X Durham. And Simpson's idea was, or maybe Deline's idea was, instead of producing a filtration on X Durham, on the coherent cohomology of X Durham, you actually produce a filtration on X Durham itself. And then it will pass to the cohomology. And so you need to make sense of that. So you need to figure out what you mean by a filtration on a space. And there comes sort of the second input, which is also due to Simpson, which is there's this dictionary between filtered vector spaces can be identified with vector bundles on the stack A1 mod GM. And the filtered derived category can be identified with the quasi-coherent derived category of the stack A1 mod GM. And so what that says is that for linear objects like vector spaces, filtrations are encoded by lifting the object to A1 mod GM. And so for nonlinear objects like schemes or varieties or functors, we just define a filtration to be a lift of that object to A1 mod GM. And so here's how we're going to do that. So we're going to lift X Durham to something living over A1 mod GM, and then I'll explain how to extract the Hodge filtration out of it. So here's the construction. Oops. So this is sort of the lambda Durham space, if you like. Lambda being sort of lambda line. So this is the lambda Durham space. So we want to produce an object living over A1 mod GM with parameter lambda, with the property that when lambda equals 1, it gives me X Durham. And in general, it's sort of an interesting construction. Now, the only sort of object that goes into defining X Durham, well, there's X, but X could be completely general, and there's GA Durham. And so the idea is to just generate GA Durham itself over the lambda line. And so here's the construction. So over A1 mod GM with parameter lambda, you may consider a deformation or a degeneration of GA Durham given as follows. So I will call this GA Durham with a lambda. And so this is going to be a cone of a certain map. So to define GA Durham, we looked at the standard map from GA hat to GA. And then we looked at the quotient. And so to define GA Durham sub lambda, we look at the standard map and then we multiply it by lambda. So lambda is the parameter on A1. It makes sense to multiply a map of GA modules with that parameter. And so you get this two-term complex. And for lambda equals 1, this is just GA Durham. But for lambda equals 0, the map is 0. So it's sort of a stacky object, which is why I said cone instead of a quotient. And so this over here is a ring stack over A1 mod GM. It recovers GA Durham when lambda equals 1, but it's something, it's the direct sum of GA and GA hat shifted by 1 when lambda equals 0. And so with this definition, the lambda Durham space is very easy to define. You just take the definition of X Durham and put lambdas everywhere. So instead of doing GA Durham, I'll do the lambda version of GA Durham. And so then X Durham sub lambda, this is going to be living over A1 mod GM. And it's defined as follows. So X Durham sub lambda evaluated on a ring R, which lives over A1 mod GM, is just X evaluated on this ring stack, GA Durham comma lambda, evaluated on R, like so. Okay, so that's the definition. Again, if it's the first time you're seeing it, it's kind of a mouthful. And so let me just draw a picture for what's going on. So here's what's going on. So here you have X lambda Durham. It's living over A1 mod GM. Now inside A1 mod GM, you have sort of a lambda equals 1. So you have a copy of spec K. The close point, or I guess it's the open point actually. And the fiber over there is our previously defined X Durham. So this is the sense in which X lambda Durham degenerates from X Durham to something else. And so what is the something else? So for lambda equals 0, I have another copy of spec K. And this time this copy of spec K comes equipped with an action of GM, because GM is the stabilizer group of the origin in A1 mod GM. And the fiber over here, I'm going to call X Hodge. And if you sort of think about what the construction is telling you, because this map over here is just 0 when lambda equals 0, what you have is a ring which is a square 0 extension of GA with GA hat shifted by 1. And so if you unwind what that means, what you get over here is the classifying stack of the formal completion of the tangent bundle of X. So it's a genuine stack. It's a stack over X. And it's the stack obtained by looking at, take the tangent bundle, look at its formal completion, and then pass through classifying stacks. But the important thing is quasi-coherent sheaves over here are sort of Higgs bundles. And quasi-coherent sheaves over here are vector bundles with a flat connection. And so this gadget gives you some way to deform between vector bundles with a flat connection and Higgs bundles. And correspondingly, one has the following theorem, which is that this picture encodes the Hodge filtration. So if you look at R pi lower star of O, So I take the structure sheaf over here, I push it down here. I get something on A1 mod GM. So this lives in the quasi-coherent derived category of A1 mod GM. Now Simpson proved that, as I said earlier, this is the filtered derived category. This is the filtered derived category over here. And under this equivalence, this gadget is just Rham cohomology with the Hodge filtration. Okay, so this is the formal picture for what's going to happen later in more exotic settings. But the idea is that we sort of came up with the definition of this ring sheaf GA to Rham, and that allowed us to define this gadget X to Rham, which gave me a way to define Rham cohomology. And then to discover the Hodge filtration on Rham cohomology, we just degenerated the sheaf into this GA lambda to Rham, so over the lambda line. And so that allowed you to sort of construct this object, which then encodes the Hodge filtration in this form. And so the upshot of this is that understanding sort of formal properties of Rham cohomology in characteristic 0 is more or less equivalent to understanding formal properties of this ring sheaf GA to Rham. And we're going to sort of copy this idea in more exotic settings. Well, now. Okay, so that was section 1 of my talk. Are there any questions? Okay, great. So this was Rham cohomology in characteristic 0. Now let's try and mimic similar constructions in positive and mixed characteristic. So let me talk about Rham cohomology in mixed characteristic. And then eventually I'll get to prismatic cohomology. Let's first just do the Rham version. So my setup is going to be as follows. So A is going to be the bit vectors of a perfect field of characteristic P. And all my pre-sheaves are going to be on p-adically complete A algebras. So we work with pre-sheaves on p-complete A algebras. So in other words, I'm doing p-adic formal geometry. So I'm going to work with p-adic formal schemes and then p-adic formal stacks eventually, etc. So I want to explain why in this setup, the Rham cohomology of smooth varieties over A can be thought of in terms of something analogous to what I was just describing characteristic 0, and why the analog of GA to Rham over here will actually tell you sort of new info, or will capture some interesting information about the Rham cohomology in mixed characteristic. And so let's get started. So here's the construction. So the notation is unfortunately going to be the same. I'll still call it GA to Rham. I hope there's no confusion. I'm working in the p-complete setting now, so there's no overlap with the previous setting. So I'm going to define something called GA to Rham, and it's going to be a ring stack. It's going to be defined very similarly to what we had earlier, except GA hat needs to be modified. So in characteristic 0, we took GA and you mod it out by the formal completion at 0. Now it's known that if you want to sort of do Rham cohomology in mixed characteristic, sort of using formal completions is not enough. You need to do something with divided powers. And so we're going to sort of replace GA hat with something involving divided powers. So GA sharp is the notation. This is the, well, first let me write down what it is. So it's perf of A adjoin all divided powers of a variable P, P to the n over n factorial. So it's the divided power polynomial ring on one generator. So if you like, this is also the PD completion of GA, or PD hull, I shouldn't say completion. PD hull of GA at the origin. And the SPUF refers to p-adic completion. So I'm always doing p-adic completions. If I'm doing sort of further completions, I will say that. Okay, and so what is the functor of points? To give an element of GA sharp of a ring R, I have to specify an element of R together with a compatible system of divided powers. So it's the functor of giving divided power elements of a ring. And so I can forget all those divided powers and just remember the element. And so you get a natural map from GA sharp to GA. But unlike what happened in characteristic 0, this map is no longer injective because those extra divided powers was extra information. If your ring is p-torsion free, there's no extra information, but as functors, it's not injective. But that's okay. We're sort of okay with looking at quotients by non-injective maps. So let's do it. So it turns out that this is an ideal. So this is an ideal in a suitable sense. So it's a DG ideal, or Drinfeld calls this quasi-ideal. It's the kind of structure that you need in order to talk about take the quotient and get a ring out of it. And so therefore, you can define GA Durham as the cone of this map. So this is now a ring stack. Okay, and so the claim I'm making is that this is going to be the object that fulfills the role played by the earlier version of GA Durham in characteristic 0. And so let's see why. So here's a definition. So given X over A, let's say it's a p-adic smooth formal scheme. I'm going to define X Durham as a presheaf on p-complete A algebras. Exactly as you might expect. So X Durham evaluated on such an algebra R is X evaluated on GA Durham evaluated on R. And now you really sort of, actually, I guess maybe no one complained about this earlier, so I will not go back to it. But I should have pointed out that when you take X as a scheme, but this gadget over here is a derived ring. It's not a usual ring. And so I'm implicitly using a tiny amount of derived algebraic geometry here because I'm looking at maps from spec of a slightly derived ring. It has a pi 0 and a pi 1 into X. And so that's why you get a stat instead of just a set. It's a groupoid because the algebra is a groupoid. And so this is the stack we're going to be looking at. So it's a presheaf of groupoids. Over here. And then the theorem, which is unsurprising, given everything I've said, is that the coherent cohomology of X Durham with coefficients in O is the Rham cohomology of X over A. The algebraic, p-adically completed algebraic Durham cohomology of X over A. And so this shouldn't be very surprising, right? I mean, like I said, I already built in the divided powers in my definition. And so if you sort of stare at the definition sufficiently and unwind what this is saying, this is essentially the crystalline Durham comparison theorem for smooth algebras over A, or for smooth varieties over A, due to Berthelot and Grothendieck. It's just a different way of presenting it, which pushes all the action into this ring over here, GA Durham. And so I don't want to prove this, but I want to explain why this perspective is useful in sort of understanding various properties of the Durham cohomology of X over A. So one of the structures that the Durham cohomology has is the Hodge filtration, like before. Another structure it has, property it has, is that there's this crystalline miracle that Durham cohomology of schemes and mixed characteristic really only depends on the mod P reduction of the variety. It doesn't depend on the original variety. And that's why you have things like crystalline Frobenius actions. And so I want to explain both those structures using this ring stack perspective. And so to get the Hodge filtration, we more or less copy what happened before. We were just supposed to multiply this map by some scalar lambda, and then see what happens in this kind of one parameter degeneration that you get. And so if you go through what the calculation you need to do in order to make sure that the special fiber is where you think it is, you need to prove the following proposition, which is if you look at the classifying stack of the tangent bundle of X, and then you look at the sharp version, meaning you look at the PD hull of the origin. So this is a gerb over X. This is the gerb you would get from this lambda deformation at lambda equals 0. Or it's a trivial gerb. And so the claim is that for this gerb, cohomology behaves well. So Ri pi lower star of O is canonically identified with omega I of X over A. for all I, and this is multiplicative. So the cup products matches up with the exterior products on the right-hand side. And so this is why differential forms show up, or the Hodge cohomology shows up on the associated gradient of whatever filtration you're defining through taking this lambda deformation. And so this is shows the Hodge filtration is well behaved. I wanted to mention this right now because I think the one thing that's slightly surprising is that even though sort of the group scheme GA sharp is slightly wonky, I mean, it involves sort of adjoining divided powers, and as a commutative ring, this has kind of horrible singularities. But it turns out that its representation theory is quite nice. So it has, for example, it has cohomological dimension 1, and you can explicitly write down what it means to give a representation of this group. It just means you have to give an object with a nilpotent endomorphism. And so it's the classifying stack of this group scheme that is relevant and not the group scheme itself. And for example, over here, this is some twisted version of BGA sharp. And that's why the cohomology that shows up is something reasonable rather than something exotic. So if instead of the sharp, I had a hat over here, I would get a mess on the right-hand side. I would get a lot more stuff. And so putting the sharp is cutting things down to size. Okay, so that was sort of my attempt at explaining why the Hodge filtration behaves well in this setting. The more interesting observation is this crystalline miracle. So I want to explain to you why, from this perspective, this object over here, so the Durham cohomology of X over A, really only depends on X mod P. So it's functorially determined by X mod P, and I'm going to do that by just articulating a property of GA Durham itself, which makes it clear that this functor itself only depends on X mod P. And so here's that property. So here's a sort of proposition. So I'm going to let W denote the sheaf of Witt vectors, p-typical Witt vectors. Then the claim is that there exists a natural quasi-isomorphism between the cone of multiplication by P on W. So sort of modding out by the ideal generated by P in a derived sense on W and GA Durham. And so let me just denote this by W mod P. And so this is not very difficult to prove. I was going to give a proof, but maybe to sort of stay on track, I will not give a proof, and I can explain it at the end if someone wants. But what it is saying is that there's sort of a very different way of presenting this ring stack, which looks sort of much more finitistic, provided you allow the Witt vectors, and it's just the Witt vectors mod P. The sort of key ingredient that powers this isomorphism over here is the relation between delta structures and divided power structures. But let's just take this as axiomatic. And so a corollary of this is the following. So X to Rham of R is identified with X of W of R mod P. But this clearly only depends on X mod P. I mean, I'm sort of looking at maps from spec of a FP algebra into X, and that only depends on the mod P reduction of X. And so therefore, it says R gamma Durham of X over A functorially depends only on X tensor FP, which is sort of this kind of slightly miraculous fact that powers a lot of crystalline cohomology. For example, it'll tell you that there is a Frobenius action on this gadget because there's a Frobenius action on this gadget, etc. And so this is something that, I mean, of course, you can just prove this directly. I'm not saying this is terribly deep, right? Like 50 years ago, we knew how to prove that crystalline cohomology only depends on the mod P reduction through some arguments with divided powers. But this is a new perspective on it, and it's a perspective that sort of is pushing all the action into these ring stacks, like GA Durham. And so the sort of upshot over here is that GA Durham, or equivalently W mod P, controls sort of the formal properties of Durham cohomology of smooth varieties over A. Just like in characteristic 0, it was this sheaf GA Durham, which was GA mod GA hat, that was controlling everything. Okay, that was section 2. Are there any questions again?
Yeah, so to get to, yeah, so you get to X drum from G drum. So if you just take a W itself, what do you get?
X evaluated on W? Yeah, I think you get.
Yeah, no, the W instead of G drum.
So I'm not sure off the top of my head, but I suspect you get something like the global version of this construction that takes a ring and produces like the free delta ring. So there's a forgetful functor from delta rings to normal rings, and this has 2 adjoints. One is given by the Witt vector construction, and the other is given by the free algebra construction. And so I suspect what you get when you do what you were suggesting is the left adjoint, the free algebra thing. So it would still like it would still have the same size as coherent cohomology. So for example, if X was affine, it would live in degree 0.
Thank you.
Yeah, thanks. Other questions? So I wanted to mention that using the stacky perspective, or more precisely using this perspective of W mod P controlling Durham cohomology, so Shubhadeep Mondal and Shijang Li and Shubhadeep Mondal have sort of figured out a lot of sort of fun results about Durham cohomology in characteristic P. And so if you're interested in this, I recommend looking up their papers. Okay, so now let's sort of move ahead. So this is now the 3rd setting of the talk, which is prismatic cohomology. And more precisely, this is relative prismatic cohomology. And eventually I'll talk about absolute prismatic cohomology. And so in relative prismatic cohomology, so this is the subject of this paper that Schulze and I wrote. I mean, we didn't really discuss the absolute version in this paper. So it's mostly about the relative version. And so the setup was the following. So you fix a bounded prism. A comma I. And I don't want to go into the definition of what a bounded prism is, but let me sort of tell you the important examples. So the key examples are the following. So, or some of the important examples are the following. So you can look at A comma P, where A is as before. So A is W of K as before. So these are the so-called crystalline prisms. And in this case, the resulting cohomology theory gives you crystalline cohomology. You can also look at what are called perfect prisms. And so the sort of prototypical example of a perfect prism is given by Fontaine's constructions. So you look at A inf of a perfectoid ring O and the kernel of the map theta. And the sort of main example to keep in mind for a perfectoid ring is, well, it could be any perfect ring of characteristic P. And probably the more interesting examples are the mixed characteristic ones. So the ring of integers of the p-adic completion of the algebraic closure of QP is perhaps one of the most important examples. And then there are sort of imperfect versions of this picture. So there are these so-called Breukissen prisms, which look like so. So you take the Witt vectors of K, adjoin a formal power series variable U, and then you look at the ideal generated by an Eisenstein polynomial. And so this is an Eisenstein polynomial. And so that means that if you mod out by this polynomial, you get the ring of integers of a local field, or of a discretely valued field. And part of the prism structure is you also have to specify a lift of the Frobenius. And so the way the Frobenius acts is phi of U equals U to the P. In the first 2 examples, because they were perfect, it turns out there's a unique lift of the Frobenius. So I don't have to worry about this, but here I do need to specify it. And so in each of these cases, whenever you have a bounded prism, like one of these 3, you get a cohomology theory out of it. And I want to explain why those cohomology theories are sort of naturally, can be understood naturally from the stacky approach. And the idea is actually going to be extremely simple. So we have this upshot from the previous section where I was saying that the Rham cohomology over A is controlled by W mod P. And all we're going to do is you're going to just replace P with I, and everything works the same way. And so let's actually carry that out. So here's the observation that sort of starts the construction. So on the category of P, I complete A algebras. So in the previous section, I was working with p-adically complete rings. In general, whenever you're working over a prism, the natural objects to work with are complete for both the p and i-adic topologies. So if I equals p, that's just p-adic completeness, but otherwise you also need to impose completeness in this i-adic direction. So on the category of p, I complete algebras R, the claim is that W, the tree sheaf of Witt vectors, is naturally an A algebra. So in other words, for any A algebra R, W of R itself is also an A algebra, and this is just the adjunction between delta rings and the Witt vectors. So the more precise statement is that the space of maps from A into R of ordinary rings identifies with the space of maps of delta rings from A into W of R. And the map in this direction is restriction from W of R to R. And so this says that whenever I have an A algebra R, there's a natural way to promote it to promote W of R to an A algebra as well. And so therefore, you may consider the ring stack, which I will call GA prism, although it should really be called GA over A prism. But I will sort of just suppress the over A in the notation. And this is defined to be the cone of the following. So you mod out W by the ideal generated by A, morally. And so if you like, it's also just W mod I, notationally, just as the previous one was W mod P. So in the crystalline case, this is just W mod P. In general, in the relative prismatic case, it sort of depends on what the ideal of the prism is. And you're modding out by the ideal of the prism. And so now you can copy the same constructions that showed up before using GA prism in lieu of GA Durham. And so let me just at least write down the definition. So given a smooth formal scheme, X over A mod I. So the formal setup of prismatic homology is that the input data lives over A mod I and the output data lives over A. So the input data is X, the geometric object lives over A mod I. I'm going to define its relative prismatization. So X over A prismatized is going to be a pre-sheaf of groupoids again on this category of algebras I'm working with. And it's defined in sort of the obvious way at this point. So X over A prism evaluated on R is X evaluated on, well, it's GA prism of R, which means it's X evaluated on W of R mod the sort of ideal generated by I in this derived sense. Is that okay? So this is the relative prismatization. It's a stack. It's a pre-sheaf of groupoids for the same reason as before, because this is a derived ring with a pi naught and a pi 1. And so therefore, the values of X on such an object is a groupoid. And it's also sort of worthwhile to sort of look at a divisor inside the stack. And so that's the Hodge-Tate divisor. And so X over A Hodge-Tate is going to be the prismatization restricted to A mod I. So just base change from SPIF A to SPIF A mod I. So this is, I'm pulling back along a Cartier divisor. And so I get something sensible. And so in the case of Durham cohomology, in Kiersik P. So in the case of crystalline prisms, this is the gadget that computes Durham cohomology over A, and this is its mod P reduction. So this computes Durham cohomology in Kiersik P. And we're going to I'm going to say a little bit about what this object looks like. And so the claim, the eventual claim is that the coherent cohomology of this stack is the relative prismatic cohomology of X. If you want to understand something structural about the coherent cohomology of this stack, because of this p-adic completeness condition I've imposed, it's enough to sort of understand structural features of the Hodge-Tate locus, of the Hodge-Tate divisor. And it turns out that the Hodge-Tate divisor has a really nice and fun description. And so I want to sort of explain what this description is. So here's kind of the key observation. Which is for any p-complete A mod I algebra. So when I restrict to the Hodge-Tate locus, I'm working with A mod I algebras. So for any p-complete A mod I algebra R, this ring groupoid, if you like, W of R mod I, is naturally a square zero extension of R by BGA sharp of R. And there's a twist here which can be suppressed if I is principal, which it is in almost all applications. And so this is a stack. This object over here is a groupoid. And so I'm saying that this ring groupoid is an extension of is a square zero extension of an ordinary ring by this complex of modules over the ring, which is supported in 2 degrees that are adjacent to each other. And this is not very hard to prove. It amounts to some manipulations with the Witt vectors, like understanding what the observation is that the image of I inside the Witt vectors of R is locally generated by things of the form V of a unit, the Verschiebung of a unit. Because the zeroth component has to be 0 because R is an A mod I algebra, and that tells you that's going to be the Verschiebung of a unit. And then once you have that, just identities involving the Witt vectors will tell you this fact. I don't want to give the proof of this fact, but let me tell you how to use it. So the way we're going to use it is by sort of saying something about this object. So X over A Hodge-Tate, if you look at the definition, you're supposed to take X, and then you're supposed to evaluate it on W of R mod I, when R is an A mod I algebra. So I'm supposed to take X and look at its values on W of R mod I. Now W of R mod I is a square zero extension of R by BGA sharp of R. And so by defamation theory, we know how to understand these objects. They're going to be controlled by X of R, which is just X itself, together with some differential data that controls derivations. And so here's sort of corollary of this observation, which is X over A Hodge-Tate is naturally a TX sharp gerb over X. The TX sharp part comes from the fact that you're looking at derivations into this, and the gerb part comes from the fact that there's a B over here. And I should probably, again, I'm suppressing the twist. I should really put a twist over here as well. And so therefore, for example, if the gerb is trivial, that just tells you that X over A Hodge-Tate is BTX sharp. So therefore, quasi-coherent sheaves on it are going to correspond to things like Higgs bundles. But it's sort of, otherwise, more canonically, it's just a gerb. It's split in the case if you have some splitting data. And moreover, so this requires a tiny amount of work, but again, it's believable given the previous sentence. If you push forward the structure sheaf of the gerb down to X, you get I forms. Because it's a gerb banded by the tangent bundle, so by duality, when you compute push forwards, and you end up getting differential forms. And so this is, in particular, this gives you a sort of a very direct and clean proof of the Hodge-Tate comparison for prismatic homology, where the existing proof was some rather complicated argument involving reducing to the crystalline case eventually. So therefore, to get a proof of the Hodge state comparison. Okay. So again, I sort of we're not using any sort of existing theory about prismatic homology. We just use the definition of what a prism is. And then all this, these consequences come out of understanding this ring stack, W of R mod I, slightly better.
Mm-hmm.
And so I guess this sentence over here already suggests that in fact there's a theorem, which is that this computes prismatic homology. So our gamma of the whole stack now, not just the Hodge state locus, coherent cohomology of the stack is prismatic homology of X. So therefore you recover prismatic homology through the stacky approach. Yeah. So maybe before I move on, I should say something about this. So the fact that this is gerb over X with this group, and the fact that it's split under the choice of some lifting data gives you a description, as I said, of quasi-coherent sheaves on the gerb. They are Higgs bundles. And so this description was also, I mean, this has been observed experimentally in the work of other people. And so this is also CF. This work of Mauro Suji. There is recent work of Yichao Tian. And then there's also August Wologotsky in the Kersik-P case. They give you all of these results give you some connection between vector bundles with flat connection or things of that nature and Higgs bundles. And this is sort of recovering several of them at least. Okay, great. So I apologize. I mean, it sounds like I'm repeating more or less the same story, just changing my ring stack slightly. So in Kersik 0, we had this GA mod GA hat. In mixed characteristic for Durham cohomology, we looked at GA mod GA sharp, which then I told you was also W mod P. And then for relative prismatic cohomology, I'm looking at W mod I, and then the theorem is always the same, that it recovers this other theory that we knew about. And so in the final part of my talk, I want to talk about absolute prismatic cohomology, where we sort of didn't know what to expect until the stacky approach came along.
Mm-hmm.
And so if you go back to the characteristic 0 picture, there were two stacks that were showing up. There was the stack GA Durham, which in that case was a sheaf of sets. But there was also the stack A1 mod GM, which was the base of my deformation. And so far we replaced the first in all of these settings. But now in the absolute theory, we replace the second one. So we have a sort of mixed characteristic substitute for A1 mod GM. So that's going to be the base over which all the action is taking place. So this is part 4. And so now we work with P-complete rings. There's no I anymore because there's no fixed prism. You're going to let the prism vary. And so the key object is the following. So let's say X is a p-adic formal scheme. The case spec ZP or SPUF ZP is already quite interesting. So the Cartier-Witt stack for X is what I'm defining. So the notation is going to be wcard sub X. So it's the Cartier-Witt stack for X, and it's defined as follows. So wcard sub X evaluated on a ring R, it's given by two pieces of data. So it's a groupoid again, and it's determined by two pieces of information. One is now we have to record that there was a prism structure somewhere. So we record that, and then we record the same kind of data that we had before. So there's a map from I to W of R alpha, and then there's a point eta in X evaluated on W of R mod I in the derived sense again, subject to the following conditions. So alpha gives a derived prism structure. And so this is a very concrete condition. So what it means is that alpha, I is an invertible module over W of R. Alpha is a map of W of R modules. And then there are just conditions imposed on the zeroth and the first component. So locally, the zeroth component has to be nilpotent and the first component has to be a unit. So it's some super concrete thing. And then eta is just a Well, I guess I should have first said what I is. So I is a line bundle on W of R. And alpha is this derived prism structure. So earlier we had fixed our prism, and so we were only recording this kind of data, but now there's no fixed prism, so we also record this gadget over here. And then wcard itself is going to be the notation for what happens when you take x equals spec CP, spec CP. And so the basic theorem, the basic comparison theorem is under reasonable conditions on x at least. So let me actually just make a precise statement. So for quasi-symptomic x, we have a natural isomorphism between the coherent cohomology of the Cartier-Witt stack for x and the absolute prismatic cohomology of x. So this was absolute prismatic cohomology is something you could define immediately once the prismatic site became available, but it was hard to sort of compute what it looks like. An example, already for spec ZP, it was tricky. And so what this is saying is that if you're interested in computing what this object is, you really just need to understand the geometry of this Cartier-Witt stack. And the geometry of the Cartier-Witt stack controls sort of the structures on absolute prismatic cohomology. And so using this, you can prove several results about absolute prismatic cohomology that we did not know before. That's not quite the direction I wanted to go in this talk, but I want to mention at least one of them. So, well, actually, let me not mention. I think I'll run over time. Let me just say that this is useful in understanding the structure of absolute prismatic cohomology. But in the rest of my talk, I want to sort of go in a slightly different direction. So one of the sort of basic vague heuristics that guides a lot of the prismatic theory is that prismatic cohomology somehow wants to be something like the Durham cohomology of x over f1. And that doesn't literally make any sense, but the idea is that sort of it really cares about the geometry of x over f1 in some sense, rather than the geometry of x over zp. So sort of the nice objects are not going to be necessarily the smooth algebras, but rather the regular rings. And so I want to actually turn this heuristic into some more precise statements. And so I want to study the Hodge state stack of x and then connect it to things like regularity. So here's the definition. So there's a divisor in the stack. So maybe let me say it this way. There's a natural map from wcard of x. Well, first of all, I can just forget the x and I can get down to SPIF ZP. Now, what am I recording when I'm working with SPIF ZP? I still have this first piece of data, the derived prism structure. And then this gadget over here has no information at all because x is the final object. So there's only one point I can use. So this part can be ignored. So I'm just recording these derived prism structures. So I have an invertible module, and then I have a map from I into W of R. Now, whenever I have such a map, I can base change down to R. So there's a restriction map to R. And so I can further base change along that map. And I get a line bundle over R and a map from the line bundle into R. So in other words, I get a point of A1 mod GM. So there's a natural map to A1 mod GM, which was just sending I to W of R to I tensor R to R. And so the Hodge state locus is going to be the pre-image of 0. So definition. wcard x Hodge state is the pre-image of BGM under the above map. And so very concretely, what it means is that you're demanding that this map over here is 0. Which means that if you think of the ideal as being, if you think of this ideal as being generated by one element, you're just saying that the 0th component of that element, the 0th width component of the element is actually 0. And so it tells you the following sort of explicit functor of points description. So wcard sub x evaluated on a ring R is the same kind of data as before, alpha, to W of R, but the map to W of R factors through V times W of R. So it lives inside the ideal generated by the Verschiebung. And then eta is as before. And so this sits inside this Cartier-Witt stack for X as a Cartier divisor. And over here, oops. If I give you an R valued point of the stack, I have in particular a map from I into VW of R. And so, well, yeah, I have a map from I into VW of R, which means that this point, sorry. This object eta, which was an element here, I can further, if I have a point of W of R valued in W of R mod I can further mod out by W of R mod V times W of R. So I can mod out by a larger ideal, and I just get an R valued point. And so there's a structure map down to X. And so post-composition, with W of R mod I to R gives a map pi from the Hodge-Tate locus of the stack to X. And the claim I would like to make is that sort of the geometry of this map, or the geometry of the fibers of this map, is sort of closely related to geometric properties of the absolute geometry of X. And so here's kind of some examples of what this looks like, and then I'll formulate a question. So maybe the first thing I should say is a proposition. So the proposition is that if X is regular, then pi is a gerb. And so this is sort of reflective of the fact that if X is regular, then we should sort of be thinking of it as like smooth over F1, whatever that means. And this Hodge-Tate locus is some analog of the Hodge stack over F1. And so the Hodge stack over F1 should be well behaved if X was smooth over F1. And this is one way in which it is well behaved. It's actually a gerb. And so I can actually tell you what this looks like in examples. So let's say X is spec ZP. So ZP should have somehow dimension 1 over the base. And so this gerb should, as I said, it should be something that looks like the Hodge stack of ZP over the base. And so it should look like the classifying stack of a group scheme, which has cohomological dimension 1. And it does. So in this case, wcard Hodge-Tate looks like the classifying stack of GM sharp rather than GA sharp. So GM sharp is the PD hull of 1 inside GM rather than 1 inside GA. And there's a mu p that sits inside GM sharp. And because of this mu p sitting inside GM sharp, you get some applications of this fact. So you get an application, for example, to a refinement of the Deligne-Luzie theorem, which I believe Luke will talk about in his talk on Friday. And I also spoke about this at the conference with Luke earlier in the summer. So I don't want to sort of spend any time on that. Let's say X is spiff OK for K over QP, a ramified extension. So it's not unramified. And so in this case, OK, the ring of integers, is no longer smooth over any base, any actual base. But nevertheless, this gerb is actually quite reasonable. So in this case, it turns out that the Cartier-Witt stack of X, or rather the Hodge-Tate locus, is BGA sharp. And so somehow the difference between unramified and ramified situation is that you're replacing GM sharp with GA sharp. And the difference between GM sharp and GA sharp is exactly that you've gotten rid of the mu p. And this is, of course, as things should be, because the mu p gives you things like Deligne-Luzie, and we know that Deligne-Luzie do not work as soon as there's even a tiny amount of ramification in the base. And so this is some prismatic explanation of why restricting to the unramified case is really important in the Deligne-Luzie theorem. If X is smooth, let's say spiff R for R smooth over ZP, then this Cauchy-Witt stack looks like the classifying stack of a non-commutative group scheme rather than a commutative one. So it looks like TX sharp, semi-direct product, GM sharp. So TX is the tangent bundle of X over ZP, and GM sharp is GM sharp. So it sort of has this flavor of something that is like D plus one dimensional, if D is the relative dimension. There's D coming from here and then one coming from here. But it's a non-commutative group scheme, so that doesn't literally make sense. Okay, so those were some examples of what the Hodge-Tate stack is. What I wanted to so I'm out of time, and so let me just end with this guess, which is a connection between this Hodge-Tate stack and certain objects that showed up in Takeshi's recent work. So there was this notion of Frobenius-Witt differentials that he defined, and then the Frobenius-Witt differentials were somehow supposed to be differentials on X relative to F1. And so in particular, you would expect that if they're locally free of the correct size, then the ring would be regular. And so there was this regularity criterion that he proved. And there's a similar kind of regularity criterion here. So I conjecture, and I think we basically know how to prove this, most of it at least, that this implication over here can be reversed. So the Hodge-Tate stack is a gerb exactly in the regular case. So there's some version of the regularity criterion in this setting. And so you might wonder what is the relation between Frobenius-Witt differentials and the Hodge-Tate stack? I mean, they're both somehow classifying regularity. And so here's kind of a naive guess for what the relationship might be based on the examples I've written above. So say X is spec R, just for simplicity, where R is a p-complete regular ring. So F, so I apologize, I'll take another 30 seconds, but I just want to write this guess. We have this map, canonical map F from the special fiber of X to the special fiber of X and then to X. And so this is the canonical map and this is the Frobenius. And so in the theory of Frobenius-Witt differentials, you don't get an object that lives on X. You only get an object that lives on the special fiber after Frobenius pullback. And so that's what this map F is. And so one can show that if you take this Cauchy-Witt stack for X, the Hodge-Tate stack for X rather, and you pull it back along F, you get a canonically trivialized gerb BG for some group scheme G over X. And so the conjecture is, or the guess, it's not a conjecture because I'm not 100% sure this should be true, but the guess is that this group scheme G should be related to Frobenius-Witt differentials. And so the guess is that if you look at the center of G, so that since G is no longer commutative, I have to do something to get something commutative out of it. I look at Z of G, the center, then I look at the Cartier dual. So the Cartier duality turns sharps into hats. So GA sharp is a weird object, but its dual is a nice object. So I look at the Cartier dual, and then I look at the Lie algebra for the Cartier dual. And this is now a vector bundle on X. And the guess is that this is the notion of Frobenius-Witt differentials on X. And so if this were true, it sort of tells you that even though this object only lives over here, it has some souped up version, namely the Hodge-Tate stack, which actually lives over X. So before doing this maneuver of pulling back to Gersig P and the Frobenius. Okay, I apologize for going over. I think I'll stop now. Thank you.
Okay, can everyone hear? Are there questions?
Yeah, so you see that speculation than question, but so at the end, so we see this link with Frobenius-Witt differential. And my motivation of studying this one is to have singular support or character cycle in mixed character situation. So I wonder, so in this prism, so maybe you have some look at some degenerate object like degenerate crystal or something. Then maybe we can expect that to have singular support of this degenerate crystal. So can you have some idea or feeling on this kind of thing?
Sorry, so you're asking how to define some notion of singular support for something like a crystal on the prismatic side of something X?
Yeah.
Well, okay, right. So I guess I didn't say this, but a crystal on the prismatic side of X is literally just, or again, so this theorem over here that prismatic homology is computed by coherent cohomology has a version that says that crystals over here correspond to quasi-coherent sheaves over here. So crystal will just give you an actual quasi-coherent sheaf, and then you can restrict it to the Hodge state locus. And so you get an actual quasi-coherent sheaf, and you could maybe contemplate the support of this just as a quasi-coherent sheaf. I don't know if that's a reasonable thing to do or not, but that would be my guess.
Yeah, that would be interesting. Yeah, thank you.
I see that other people have questions. I can't quite figure out how to localize them. Maybe anyone who has a question could speak up.
Yeah, last you can. Yes. Yeah.
Okay. So you have this map from the Cartier-Witt stack to A1 mod GM, which must give you a filtration on absolute prismatic cohomology. Is that right?
Yeah.
What filtration is that?
This is the p-adic filtration.
It's the p-adic filtration, so the Nygaard filtration.
Yes, I don't think you can get the Nygaard filtration just as a map from wcard to A1 mod GM, because it's not a filtration by quasi-coherent sheaves.
Oh, I see. Okay.
But you have, I mean, Drinfeld has this enlargement, sigma prime, which does have a map to A1 mod GM, and you can sort of prove that, I mean, like associated to any X, there's a quasi-coherent sheaf on sigma prime. And then that corresponding filtered object is the Nygaard filtration.
Yeah. Thanks.
I'm sorry, there's at least another question. I can't localize it. Somebody else is asking a question. Can they go ahead and ask?
You can make a question.
Yeah, I just typed it in the chat, but I can't read it. Does it imply that the Cartier-Witt stack can be reconstructed using analytic geometry of F1 if X is regular?
I don't know how to parse that question. What does analytic geometry of F1 mean?
Like we can study some analytic stack over F1.
Sorry, but what does F1 mean?
You just spoke about that if X is regular, we can.
Right. Sorry, maybe I should have made this clear. I'm not claiming I'm defining F1, right? Like there's no F1 I know how to define, but you can pretend that there was an F1 and then use that to come up with some guesses for what things you do know how to define look like. And so that was what I was trying to do at the end of the talk. So I don't know anything about like how to actually define some geometric object over F1.
Okay, thanks.
So I think the next talk is scheduled for quarter after the hour. And so maybe we just wait 5 minutes or I think that way we stay on the schedule. So the next talk will be in about 6 minutes.
Yeah, thank you very much.
Thanks.